Democrats and Republicans actually agree on this. Last time I checked. Speed of light, same everywhere in the universe. So those are universal constants. So you basically just get this nice, simple, direct connection between that difference between the energy levels and the emitted wavelength. So that's the reason we get different actual emission line wavelengths when we look at hydrogen versus helium. It's because, again, the spacings between the energy levels are different. Okay, I think I actually included with this slide last time, which is on the top. It's actually radiative excitation for the photons coming in, followed by radiative de-excitation. So this is a scenario where the atom borrows the energy of the photon and then creates a duplicate photon in the de-excitation, except the direction is different. So that's another thing that's happening there. A modification of this is if we absorb enough energy to pop the atom into the second excited state, then it actually has two options for what it does. It could actually decay back to the ground state and produce a photon with the same energy as the input photon, but a different direction. But it has another option because it's in the second excited state. It could, optionally, decay to the first excited state and then to the ground state, emitting two photons in random directions. But remember that the energy of these two resulting photons here, because of energy conservation, energy of those two photons still has to add up to exactly the energy of the input photon. But anyway, this is basically a situation where we could create emission or absorption lines depending on the direction that we're looking at the gas. Here, we're looking at actually heated gas, so we're seeing emission lines. Okay, so again, working our way through this. Hot bulb, continuous spectrum, heated hydrogen gas, we get the emission line. So this is the case we were talking about a moment ago where we have heated the gas, the atoms are slamming together, they get excited, they de-excite by emitting wavelengths, but just certain wavelengths that correspond to the energy, E2 minus E1. And so what you get on the screen is just the specific wavelengths that correspond to those photons that are created in the de-excitation that occurs after the collisional excitation. So this heated hydrogen gas is cooling down. We don't keep heating it. There's no Bunsen burner there. It'll cool down. And the reason it's cooling down is because its energy is flying out in the form of those emission line photons. So that's one way of getting emission lines. The other way, again, is by looking at a cool gas at an angle. Okay, so this is the part that we still want to kind of carefully explain in detail what's going on here. Essentially, we're going to get absorption lines over here because some of the wavelengths in the hot bulb's emission, some of those wavelengths are going to be borrowed by the atom. It's going to lead to excitation, right? This is not collisional excitation now, it's radiative excitation. Those radiation wavelengths are leading to the excitation. So we're only removing certain wavelengths, and now we have excited atoms in there. Excited atoms, and they're eventually going to de-excite and emit radiation, but it's going to be in a random direction, not the original direction into the slit over here. So when the de-excitation occurs, the de-excitation photons go in all sorts of directions, and those are the ones that pass through the slit here and create the emission line. So we're seeing emission lines on the off-axis spectroscope because the only photons that go through that upper slit are actually just a small fraction of these de-excitation photons that go in random directions. Okay, so another slightly different way of looking at this. We have our white light, our cool gas. The photons get absorbed in excitation, and then they get sent out in random directions. So these photons out here are the de-excitation photons being sprayed out in random directions. The only photons that go through spectrograph 2 are just a small fraction of the de-excitation photons. Most of them go in other directions. But a small fraction go in this direction. But you see emission lines over here. They're very weak emission lines, but you see them because there's no competition with anything else. The only photons that go through spectrograph 2 are just those emission line photons. So because there isn't any other white light, contaminating thing, you actually can see them. Over in this direction, you get the absorption lines. So one way of kind of summarizing this is if we collected together all of these emission line photons, these de-excitation photons, if we just could collect them all together and focus them back using mirrors or something, they would perfectly fill in these black lines. Because the photons that are missing from the absorption lines have just been sprayed out in random directions. So if we could collect them all together again, and get them back moving in the same direction they were moving originally, they perfectly fill in the absorption line. So here we have again a dramatization. The yellow light goes straight through, the green light goes straight through, and now this is like here. Here we have the red. Oh, look at the black. Thank you. And you use your sun to applaud, I can see that. But okay, the red again gets borrowed, sent out in random directions. So a little bit of it goes down here, forms the emission lines. A little goes here, but very little, so it's not enough to fill in that absorption feature. So you still see that dearth, Vader, of red photons. You see that black feature. And up here, well, some of the red photons went up there, but we haven't detected it. I think I probably hit that hard enough. Skip over that. Okay, so anyway, I'll try to go over this before the next exam, but I'm going to ask a number of questions about all that stuff you just talked about. That whole scenario, why do we have emission lines in some cases, absorption lines in others, what happens to protons, radiative excitation versus collisional excitation, blah, blah, blah. So we'll go over that again for the actual exam. Okay, there's another thing that can happen, which it can occur if we send in too much energy, way too much energy. Now, if you just send in the wrong amount of energy, it just gets ignored. Like the yellow photon passes through the hydrogen atom, right? But suppose you send in a ton of energy, it's not really ignorable anymore. You can actually disrupt the atom completely. And that's called ionization. So if we send in way too much energy, and actually what we're talking about here is not visible light anymore, but it's a higher energy form, ultraviolet radiation. If you shine ultraviolet radiation on atoms, or if you can go even farther and shine X-rays on atoms, that will be so much energy the atom can't do anything with it but just falls apart. It can't, it's too much energy to cause actual excitation. But it's so much energy it completely removes the electron from the atom. Now, the electron and proton have an electrostatic attraction. They're opposite charges, so of course they're attracted to each other. But we're dumping in so much energy it completely overwhelms that attraction, just blows the atom apart. And so we get an ion. That's what we call this ionization. We have an unbound electron and we have an ion. So this is ionized hydrogen gas right here, which is just protons and electrons. We can also have recombination, which is when you have, in this case, protons and electrons zooming around, and occasionally they'll recombine, and it's exactly the reverse process where they recombine and then energy comes out. So we call that recombination. So we have ionization and recombination, which can occur in situations where there's very high energy radiation involved. Okay, now we're actually kind of going back to before the discussion of the real physics of what's going on. We're going back to 1859 here, when the internet wasn't invented, hadn't been invented, on the drawing board. I mean, they didn't even have sticky notes. I was going to say it was on the sticky note, but it wasn't on the sticky note. It was around sticky note. I think there might have been that. But anyway, my point here is that we're going back, around a full 50 years before the whole theory of atomic structure worked out. So we're going back to a time when they didn't understand any of the stuff we were just talking about. They didn't understand energy levels. They didn't know that they didn't even know there was a nucleus in the atom back in 1859. So Kirchhoff's laws are actually just a set of empirical observations of what we see in the laboratory when we set up different types of experiments. So it's sort of like if you go back to Kepler's laws, when we're talking about planetary motions. And Kepler deduced these patterns. He didn't know what was going on really. It's the same thing here. There's a deduction of different patterns. Oh, thanks. I take decaf. Cream and sugar? Thanks. Use my buddy with me. Get it. Make it snappy. Lay on. Okay, so there's a few Kirchhoff laws here. One of them is that hot gas at high density and pressure actually goes to a continuous spectrum. So this is actually sort of a corollary or kind of a parallel thing to what we were just talking about a moment ago about one of the ways of generating emission lines is by heating a gas, right? Remember that if you ever forget about that, just think about the light bulbs in the ceiling here, because there's gas in there that's being heated by electricity and they're producing emission lines. So if we pass the light from these bulbs through a prism, we'll actually see emissions on a continuous spectrum. But anyway, if we take hot gas at very high density or pressure, much higher than the density and pressure of these bulbs here, it acts kind of a little more like a solid, and what you get is non-emission lines, but you actually get a continuous spectrum. It acts a little bit more like a solid body, like if you take a piece of coal or a piece of iron or something, you heat it up, you don't get emission lines, you get a black body spectrum, right? That's basically the idea here. If you have a dense enough gas and you heat it up, it acts sort of like a solid, and you just get a black body spectrum, non-emission lines. So remember to keep that in mind, because when you heat a gas, you don't necessarily get emission lines. You could get a continuous spectrum depending on whether it's dense gas or not. But what actually happens physically, which Kirchhoff had no idea what was really going on, you just observe that if you heat a gas that's dense, you get a continuous spectrum. But what's really going on is we're getting a certain level of ionization, and the photons that are produced when we have an ionized gas, which we call a plasma, we can produce photons when electrons and protons that are free pass by each other. But the photons that are produced don't have precise energies like what we saw in atoms, simply because this isn't an atom. So there actually aren't specific energy levels anymore, because you have a free electron and a free proton. They can go by each other, and basically anything can happen when an electron goes by a free proton. So the photon that comes out is not a quantized photon, because there aren't quantized energy levels. So anyway, in a situation like this, we actually will produce photons at many different energies, because many different kinds of collisions are going to happen randomly with gas. And what we get is many different energies, and when we collect those photons together, we have a continuous spectrum. So the hot gas at high density and pressure actually is going to produce black